Hey everybody, and welcome back to Algebra 2 Online. So today I want to talk about some application problems related to logs and exponentials, and I've got a few different examples. We're going to mostly do examples in this video. To start off, there's a very famous problem that I did not come up with. Someone much more clever than me probably did. But I always teach this problem at some point in this unit, and I always think it's kind of fun. So totally unrelated to applications of logs and exponentials, but just fun nonetheless. So what I want to do is I want to take this thing and I want to rewrite it just so m is on both sides. That's the goal, okay? And at first it might look like that's not possible because we only got one m here, but you actually can do it. And you can't just cheat and be like, okay, well, that's easy, plus m, and now you're done, right? You can't do that, okay? Over here I have my little conditions. You can't just add, multiply, subtract, blah, 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 m to both sides. You only have what I gave you here, and you just gotta manipulate this equation and get m on both sides. So I highly suggest you pause the video and try it. And I've got this hint down here that this is the wrong time of the year to do this problem. Hint, 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 hint. Okay? All right. Hopefully you tried it. I'm going to just get into it now. So first thing I'm going to do is multiply by the denominator of my fraction there, so I can get rid of the fraction. So I have r squared equals natural log of x over m minus sa. And I think I'm also just going to write r squared as r times r. Right. Then I want to get rid of the log, so I'm just going to exponentiate both sides, right, with e. So I'm going to have e to the rry equals x over m minus sa. Now I'm just trying to get to this m so I can work with that. And now, I'm just going to multiply both sides by m, okay? And if I do that, I'm basically going to get m e r r y equals x minus, and it looks like Sam, but of course multiplication is commutative, so it could be m-a-s, right? And then, it says Merry Christmas. And my hint was written in green and red, and so it was kind of a good hint, I think. But yeah, that's kind of a famous problem that I once saw around Christmas time at some point, and I've always liked it. So there you go. That thing is just Merry Christmas or Merry Xmas hidden in that weird natural log equation right there. All right. So the main thing for today, like I said, is to talk about applications of exponentials and logs. And the two kind of basic equations that you get are given right here. So there's a basic exponential growth equation that is just a function q of t. So it's a function of time. And I'm actually going to talk about what all these variables are. But this thing right here is actually one specific variable, and then that is e, like the exponential number e, and then rt, and then there's exponential decay, which looks very much the same, but you have a negative in the exponent, right? And so the negative, what that would do is if you did the reciprocal of e, right, it's going to be 1 over e, and you're going to have rt, right? So this would be decay because that number is less than 1. 1 over e is less than 1, so it's going to be decay. So these things are physical properties in the world. So Q of t is literally what I would say is the end quantity that you have. So if you're talking about exponential growth of bacteria, this is the result, the end amount of bacteria you have after a certain time t. And I've already said that once, I might as well put that in here. Another one that's pretty intuitive. A lot of times it's R, so R is rate. So there's going to be like growth rates or decay rates for these problems. The last one in here, this little Q0 thing, this is actually read, you would read this Q naught, N-A-U-G-H-T, I think is the correct way to spell that. But Q naught is basically just your initial quantity, okay? So just like in all like real physical problems, like if you're doing like the growth rate of some sort of bacteria, right? There had to have been some bacteria to start off with, so there was like an initial quantity, and then after like a growth rate that you know, and some time, you could end with a certain quantity, right? So all the application problems that we're going to do are basically going to follow one of these two structures. It's either a growth thing, and it's going to be just built out of taking that exponential number e and raising it to the rt, rate and time, and then all of that is multiplied by the initial quantity, or initial quantity times e to the negative rt. And the negative will just, of course, make it a decay problem rather than a growth problem. All right, so just going to go through a few examples right now. So this first one is actually a bacteria growth problem. So a certain strain of bacteria is growing on a kitchen counter, and it doubles every 5 minutes. Assuming that you start with only one bacterium, how much bacteria could be present at the end of 1 hour and 36 minutes? So the first thing you should always think is it exponential growth or decay? And this is pretty clearly, right, exponential growth. So I'm going to use that Q of t equals like Q naught. Sometimes we read it Q sub 0. It's kind of like the 0 is like time 0. It's like the initial time. And then e to the rt. And then, you know, if we just go and plug in what we know so far, so we want the end amount. This is like going to be my thing I'm solving for, right? I know I start with one bacteria. I know I got E in the problem. Now I don't know the rate, right? And I do know the time. The time is 1 hour and 36 minutes. You should never mix units though. So in applications, you never put in hours and minutes like that. You would just put in one or the other, or you could put in like seconds. You could put years, whatever you want, but you have to keep the unit to be fixed, one unit. So I'm just going to put it in with minutes, right? So I'll just do 96 minutes, okay? That's what I know, but obviously that's an issue because I've got two unknowns, right? So I have to solve for this rate up here. This is going to be like the little side problem that I need to do, okay? And that comes in with this whole idea that it doubles every 5 minutes, okay? So we know that if we started with one, right, bacteria, we're going to get two bacteria after 5 minutes, right? So again, if you're just thinking of this equation, I'm just plugging in one initial bacteria. It doubles to two bacteria after 5 minutes. You could technically do like anything as long as it represents doubling, right? Like you could do 10 here, and then you would just have to have 20 here, because then that would still represent doubling after 5 minutes, right? But I'm just going to do the simplest one. I'm just going to do one doubling to two, okay? And that's nice because really this is the same thing as e to the 5r. And this is a super nice equation to solve. We just do ln of 2. We get 3r. We divide by 3. And that's my rate. That's not a 3. I just can't read my handwriting. I'm sorry. That's a 5. So divide by 5. Now it's good. So honestly, now we basically have it. Just go back here and go pop that ln of 2 over 5 in. And this is why I taught you guys how to use your calculators before, because at this point now I think it's good to get answers with the decimal, because it's gonna they're physical things now, and it makes sense to analyze the decimal part of it. Whereas before, like, we might have just been fine with that as a number to like the solving a log equation or something. But now, like, we're talking about bacteria, and so we want to know, like, the amount exactly, right? So if you just literally go to your calculator and do e raised to this times 96, okay, you should double check that you can get all this, because it is kind of a decent amount of plugging in, but you would basically get 602,248, and then you get 0.76 roughly bacteria. But these are real world, like, physical problems, right? And this 0.76 does not make sense. Basically, there were like some pregnant bacteria or something like that, but there were parts of bacteria that were not full bacteria yet, right? So the correct answer really should be, the end amount is there's 602,248 bacteria sitting on that countertop, which is absolutely disgusting if you think about it. This is very real world numbers. Certain bacteria can definitely double and split every 5 minutes. And so even just after like an hour and a half roughly, you have a lot, obviously, right there. This is why exponential things are important to study, because we need to know how quickly things grow. But this is kind of the general feel of these problems. I've got a few more that I just want to do. But you basically just think about, are they growth or decay? Plug in what you know. Sometimes you will have to solve for the rate, like we did over here. And then we might have to plug that in and like then get an answer that we have to like analyze a little bit. And, like here we have to realize that that decimal doesn't make sense. So you would only want that answer. All right. So in this problem, it says a radioactive element, potassium-42, is often used actually in biological experiments. I was actually pre-med when I went to college, and I would use potassium-42 for a lot of stuff. But it's used because its half-life, and I'll explain what that is in a second here, is actually only 12.4 hours, which is quite short. And that's useful in like a lab where you're trying to do an experiment. So you would use this thing, this potassium-42 radioactive element thing, and it having a short half-life, because actually we're about to do a problem that has a very long half-life, and long ones can be on the orders of like 1,000 years sometimes, but this one's only hours. So you can go into the lab, set up an experiment, and just like check on it the next morning, and some stuff will have happened. But the question is basically if you have a how much of a 2 gram sample will remain after 18 hours and 45 minutes, okay? So let me explain this half-life thing here for a second. So half-life is, literally I would just define it this way. So it is just the length of time for half of the element to decay. So, like if you had 7 grams of potassium-42 starting off in the lab, and you go 12.4 hours, well, then you're going to have 13.5 grams of potassium-42. Basically, there's just like a natural process of decay, and I'm going to let your like chemistry and biology teachers talk about it. It takes quite a while to explain, but it's a very natural occurring phenomenon. Like some of the famous examples that you might know of is like there's like these places like the Chernobyl, and Chernobyl, there was sadly like a radioactive, there was a reactor that basically went and exploded and released a bunch of radioactive elements and basically decimated the land. And you can't like grow crops and all sorts of bad things. You really can't even live there. You are starting to get to the point actually where you can visit it. And the reason it's actually getting better is because there's like a half-life involved. So there's a half-life to those radioactive elements, and they're slowly decaying and becoming more stable and disappearing. It will never fully be gone, right? This is that idea like if you walked, like if this was some sort of wall and you walked halfway to the wall every time, right, you're never actually going to get to the wall. And so it's kind of a weird property. But things that are radioactive will never fully leave, but you will get to a point where, in a sense, when you get close enough to the wall, you can basically start growing crops. You can start living there, those kind of things. So I actually once looked it up, like when will Chernobyl be safe? And it's actually quite a while still. But that's the idea of half-life. It's just literally a measurement of the time it takes for half of the thing to basically decay and disappear, and just like break down with natural properties. Okay. So this one's definitely a decay problem, all right? And we want to know how much of the sample we have at the end. So it's another one where we're solving for Q of t. We know we started with 2 grams of the sample, right? We know we got a decay, so we got a negative up there. Again, we don't know the rate, okay? And we do know the time, right? We want to know how much will basically remain of this after 18 hours and 45 minutes, right? And so 18 hours and 45 minutes you could put in as 18.75 hours. It's like a nice minutes to hours, right, connection there. So you could just put it as 18.75. So now basically what we got to do is just kind of like the last problem, we got to solve for this rate, okay? And that's where the half-life comes in, all right? So we know that if we let those 2 grams decay for 12.4 hours, right, then we know that we would have half as much left over, right? Because that's what it means to be to have its half-life be 12.4. So these 2 grams decay to 1 after its half-life, right? And that gives us a thing that we can solve, right? So we can have 1/2 equals e to the minus 2.4r, take natural log of both sides, get negative 12.4r, divide by negative 12.4, and that is going to be your rate, okay? So whatever crazy number that is, okay, if you just go and take that number and you pop it in right here, then again, go to your calculator, plug everything in. I highly suggest you don't round things as you're going like this. You want to keep your answers as exact as possible, because if you round it here and then put it in and then round it again, you're going to get an answer that's further away from the correct one because you've rounded too many times. But if you go and plug all that in, which you should check just to make sure that you get the same things I got, you get something that's about 0.701 grams, okay? And in these like application, like real life problems, I highly suggest you think about your answers. So like if you got an answer that was like 4 grams, that would be an issue because it should be decaying, right? If we started with 2 grams, we would never expect the answer to have more than 2 grams. Like if it's decaying, it's got to be less than 2, right? And you could even do better because half of it should be gone after 12.4 hours, right? So if you're going more than the half-life, 18 hours and 45 minutes, then you should have less than 1 gram, right? Because you get 1 gram after its half-life. But then if you go more than it, right, you should have less than 1. So that's it. That's like the way that we can kind of do like a decay problem. So this is going to be the last one I'll do. I think once you kind of see 1 or 2 of these, you start to kind of get the idea of them, but let's just do another one. So this one says, a paleontologist examining the bones of a prehistoric animal estimates that the bones contain 2% as much carbon-14 as they would have contained when the animal was alive. And the half-life for carbon-14, sometimes just called C14, is right here. And the question is, how long ago did the animal live? Okay. So this is actually a very famous technique, and carbon-based life forms, like we are, and mammals and all sorts of things, They have a natural like process related to the sun. Like if you've ever been exposed to the sun, then there's actually like the sun rays come in your activate some of the carbon in your like body, in your hand and face and everywhere, and basically knocks some of the electrons off that element and gives you carbon-14. And that's a really, really rough example. And again, you really need to take some biology and some chemistry to understand what's going on. But the thing that's nice that paleontologists like is that this carbon-14 stuff does not decay fast. The half-life of it is 5,700 years. So what they literally do, like if they go find like a mummy or something in Egypt, they know that mummy was like a mammal, right? And it should have carbon-14 in it. And they can literally just scrape off a little bit of the bones and they can be like, well, it should have, this much carbon-14, but we notice that it contains 2% as much as carbon-14, let's say, as it should have had when it was alive. So how long has it been decaying, right? And so you can find out the age of things by analyzing how much of this carbon-14 stuff is in carbon-based life forms, which is kind of cool. Fairly straightforward, honestly, to solve it. This one, like, you just want to know the time, which is a little bit different from the last problem. So we know that there's just 2% as much carbon-14, right? So, like, if we started with 100 grams, let's say, then we would be at 2, or if you started at, like, 1, you'd be at 0.02. If you started at X grams of carbon-14, you would be at just 0.02x, right? It really doesn't matter what you put as like the initial here and as the end, as long as it represents 2%, right? Like a ratio of 2%. So what I would just do for simplicity is let's just say it was a 1 here, right? Then there should have been 0.02 carbon-14 left over. We know we got an E. We know we got a negative. Again, we don't know the rate. Okay, we'll get to that in a second. And we don't know time because that's literally what we're solving for. All right. So to do the rate part, that's where we're going to use this half-life, just like before. So if we started with, say, 2 grams or something of carbon-14, we would have 1 gram of it after 5,700 years, right? And so we could use that equation to solve for R. So just going to divide by 2, take natural log, and then divide by negative 5,700. So natural log of a half over negative 5,700 is your rate, whatever decimal that is. So then again, just like some of the last problems, we take this, pop it in here, right? And basically we'll be done. So here, so we got 0.02 equals E to the natural log 1/2 all over negative 5,700 times T. Here, if we wanted to solve for T, right, we should take natural log of both sides. And if we take natural log of both sides, then you can cancel off the E on the right. So you got natural log of 0.02 equals natural log 1/2 divided by negative 5,700 T. And so then you can just go and multiply by like the reciprocal of this just to solve for T. So as like a final answer, you could have negative 5,700 over natural log 1/2 times natural log of 0.02 is equal to T. And again, you could plug this into a calculator. If you do, you get like about 32,169.98 years. And it's years because those were the units for the half-life. So the units here will match the units here, right? So really, either one of those you can do. This is the exact answer, right? And then this down here is the like approximate one. But I think that should be enough to practice some of these. You know, they all kind of have the same feel about them. Basically, you're putting some two quantities in here, right? Beginning amount, end amount, right? And it makes sense the end amount's here because it's like you plug all this stuff in, we factor in the rate and the time, and you get out something over here, right? And it doesn't obviously need to be like, I don't know, sometimes students don't like that the output's over there. Like I could absolutely have put 0.02 on that side, right? Don't think it has to be, like it can be input stuff and then output on the right. Doesn't matter. And then the rates almost always typically just come from something like half-life, or, you know, if it's like a growth problem, like the growth factor here is that it doubles every 5 minutes. So you're taking that into account with E, and you're going to get natural log of 2/5 is the rate there. These rates, too, should be like decimals, right? It would be very weird if they were not decimals. They are rates of growth. And so, you know, like this one down here, if you go and do it out as a decimal, you're going to get about 0.00012. And it would be odd if you got those to be like things over 1, basically, if you're doing some sort of decay. But that's about it. Hopefully this helped and you can do some of these on your own.